The flow rate through a given pipe is defined as the volumetric rate at which a liquid is flowing perpendicular to the pipe's cross-section. The flow rate in meters cubed per second is equal to the average fluid velocity in meters per second times the cross-sectional surface area of the pipe. If the cross-sectional area of the pipe is changing, then the continuity equation can be used to get the average fluid velocity at any cross-section within the pipe. This is achieved by realizing that the flow rate within the pipe is constant. The velocity times the cross-sectional area is then substituted for the flow rate. Finally, the equation is rearranged to obtain the average fluid velocity at any location within the pipe. Knowing the fluid velocity at any other location and the pipe's cross-sectional areas. In English units, the volume flow rate is given in units of cubic feet per second. To convert the flow value from meters cubed per second to cubic feet per second, you need to multiply by 35.315. To convert from cubic feet per second to meters cubed per second, multiply by 0.028317. Sometimes the flow is also expressed in units of gallons per minute or GPM using the shown conversion factor. There are various ways to measure the volume flow rate. In this section, we will cover a few measurement methods. 1. The direct method. 2. The point methods. 3. The positive displacement methods. 4. The method with restrictions. 5. The fluid momentum methods. And lastly, the wave measurement methods. Direct measurement is the simplest way to measure the volume flow rate. The volume flow rate is calculated by measuring the time that it takes for a certain volume of liquid to be filled into or discharged from a tank. The advantages of the direct measurement method include: 1. It is simple to implement. 2. Does not require expensive measurement equipment. The only equipment needed is a stopwatch and a way to relate the volume of fluid in the tank to the depth of the fluid. The disadvantages of the direct method include: 1. Low accuracy. 2. The direct method is only able to measure the average flow rate. Instantaneous changes in the flow rate are not detectable by this method. 3. Depending on the piping system, it might not be possible to use direct method. 4. It is difficult to automate this method. Point measurement method measures a flow property at a specified point. The flow properties that are measured are pressure and velocity. The Pitot probe is made of a tube that has a 90-degree bend in it. The tube is positioned parallel to the flow. It has an opening at its tip that is subjected to the fluid's stagnation pressure. When the fluid impacts the tip of the probe head-on, the fluid velocity drops to zero, and all of the kinetic energy of the fluid is transformed into pressure energy. When this happens, the pressure at the tip of the probe is equal to the stagnation pressure at this point within the flow. The opening at the tip of the tube is connected through a passage within the tube to a pressure measuring device that reads the stagnation pressure. The Pitot probe also has a number of holes around its periphery downstream of the probe's tip. These holes, being positioned perpendicular to the flow, measure the static pressure at that point. The static pressure holes are connected through another passage within the tube to a pressure measuring device that reads the static pressure. The dynamic pressure is equal to the stagnation pressure, which is the pressure at the tip of the Pitot tube, minus the static pressure, which is the pressure that is obtained from the Pitot tube holes that are perpendicular to the flow. From this equation, we can calculate the speed, which is equal to the square root of the stagnation pressure minus the static pressure times 2, divided by the density. It should be noted that a Pitot tube measurement is used to obtain the speed at a single point within the flow. In order to obtain the flow rate, the speeds at several points along the pipe's diameter must be obtained, and then integrated over the pipe's radius to obtain the overall flow rate. The advantages of the Pitot tube include: it is one of the most accurate methods of measuring flow velocity. It can be moved to various points along the pipe's diameter to measure the entire velocity profile within the pipe. However, the Pitot tube has some limitations that include: difficulty of automating the measurement process in order to be suitable for industrial use. The need to precisely orient the probe with respect to the flow in order to get accurate readings. The Pitot tube can be easily damaged, or clogged if used within a flow that contains suspended particles. The location on the pipe where the Pitot tube is inserted can cause leakage. This is due to the fact that the Pitot tube cannot be rigidly attached to the tube since it has to be free to rotate and move along the pipe's diameter. This is especially true for high-pressure flows. The main component of the thermal anemometer can either be a thin platinum or tungsten wire or film that is placed within the flow. The wire or film is connected to an electrical source that passes current through it, which causes the wire or film to heat up. The wire or film is either heated up by a constant current, or kept at a constant temperature by varying the voltage across it. When the flow passes over the wire or film, heat is transferred from the wire or film to the flow. A higher flow velocity would cause more heat to be transferred from the wire or film to the flow. Knowing the temperature of the flow, the current passing through the anemometer, and the temperature of the wire or film, the flow velocity at that point can be calculated by a controller using convection heat transfer relationships. The advantages of using a thermal anemometer include: high accuracy, an easily automated collection procedure, and a high-frequency response allowing measurement of turbulent flows. The disadvantages include: high cost, sensitivity to the orientation of the wire or film with respect to the flow. The wire or film are fragile, and the wire or film can accumulate debris or dust in a dirty flow, which would impair the measurement. The thermal anemometer is limited to gas flow applications. The laser Doppler anemometer, or LDA, uses two laser beams that are at an angle with respect to each other, to measure the velocity of the flow. The two laser beams are within an imaginary plane that is parallel to the flow direction, and they intersect within the flow. At the intersection point, a fringe pattern is formed due to the interference of the light waves from the two beams. As the particles pass through the fringe pattern, they reflect the light from the fringe lines. When a particle passes through a fringe line, the light intensity reaching the detector varies. The frequency of the resulting flicker in the light intensity at the detector can then be used to calculate the velocity of the particles perpendicularly to the fringe pattern. The advantages of the laser Doppler anemometer include: the readings are unaffected by changes in temperature, or density of the flow field. And there is a very high frequency response for the measurement. The disadvantages of the LDA flow measurement technique include: high cost of the equipment. It is limited to use in transparent fluids such as most gases and clear liquids. Its accuracy depends on how precisely the laser beams are oriented with respect to the flow direction. Particle image velocimetry, or PIV, uses an optical method to measure velocities of the flow. The typical apparatus consists of a camera, a laser, and the fluid. Particles will be introduced into the flow. The laser beam will shine on the particles, and the particles in the fluid will reflect the light to the camera. In order to measure the velocity, two images are needed. The images will be split into a large number of tiles. Finally, the velocity will be calculated by measuring the time between those two shots.